then ends up there, what you see is very strong Coulombic attraction between the two parts. And that's why polar surfaces tend to attract polar solutions to them. And that greatly reduces the free energy of the surface. And as a result, the water molecule prefers to be in contact with the surface rather than to form a drop. Okay, so so the water molecules will then just I'll draw it like waves, even though it's far too small to be a wave. But the water molecules will just smoothly coat the surface. If, on the other hand, you have a contamination layer where you have, say, hydrocarbons that are poking up from, say, a polymer contamination, or somebody put, cologne on in the morning, and they went into the clean room, and the cologne basically comes off on the surface, so they put an aftershave, or they have a shaving cream that has an odor to it. Any of those things is going to come off on the surface, put hydrocarbon down on it, and then when you try to deposit water, the water, which is highly polar, has a choice now between bonding to the surface molecule or bonding to other water molecules. And the water will, in general, prefer to bond to other water molecules that are also polar. Okay, so these are not strong covalent bonds. They're weaker bonds, but they're still stronger than the bonds to the surface. And so you end up with I've over-exaggerated. It doesn't actually form a full sphere. It'll wet the surface a little bit, depending on the relative energies that are involved. So the point is that balling up is what happens if there's a little bit of grease or oil-like contamination on the surface. Yeah?
What if the contaminants are hydrophilic?
What if the contaminants are hydrophilic? Then you wouldn't see them. Contaminants, in a contaminant, this technique wouldn't work. Contaminants are typically so you could have like metal contamination, for instance, in a wafer. This isn't going to notice that. I'm just trying to think of a strongly hydrophilic contaminant that you might have. I mean, I guess in principle you could make a polymer that was strongly hydrophilic, but generally polymeric systems, complex organic molecules, I don't want to overstretch here, but there's a lot of them that are hydrophobic. So more hydrophobic than water anyway. So most of the contaminations tend to be hydrophobic. And there are other ways to look for contamination. This is not the only way. There's one other thing I wanted to mention, but I'm assuming we'll come to it. All right. So I mentioned here the attraction between the surface and the substrate. I took a different approach from the notes. So the notes basically start building it up from the point of view of two atoms and say, okay, if you have two atoms, all right, they see an attraction to each other, like a molecular attraction, and if you plot their free energy versus, the potential versus the interatomic separation, you see some potential. So they can't actually overlap with each other because you start to force electrons into orbitals that already have full occupancy. But as they get close to each other, there is some quantum mechanical tendency for the two atoms to attract, or there could be at least a dipole-dipole van der Waals type attraction. So there'd be some tendency for them to want to bond, and of course if you add a third one to this mix, the fourth one, that attraction gets even a little bit stronger. So this is for 2 atoms. This is for more, right? So say all around it. And then if you think about what happens at a surface, right? At a surface, the atoms see an attraction to each other, all right? But there is a missing atom at the surface that it cannot have that attractive potential to. And so for a surface, I'll do it with a dashed line here. Call this Vs for the surface. There's going to be a little bit less, so this would be like a bulk condition. There's going to be a little bit higher potential there than in the bulk. And that difference in energy between a fully passivated bulk atom and a surface atom is basically the energy cost of having a surface present. So in the attempt to minimize that energy cost, systems typically attempt to minimize the surface area, and you end up with spheres, because spheres have minimum surface area. And depending on the relative energy cost of, say, the water, the air, and the surface, you can go from extremes where you really form a full sphere. It balls up completely. In this case, the system gains very little advantage by being bonded to the surface, to you basically completely wet the surface. So which of these would correspond to a polar surface for water? The one on the right, right? This is even on. This would be called hydrophobic, and this would be called hydrophilic. And people can also call this oleophobic, oleophilic. Okay, so that's the tack that notes take place. One thing I would mention is that this ideal model of forming a sphere is only true for very small drops. For large drops, gravity has an effect and it distorts the shape of the drop. Okay, one little point of sometimes confusion is, if you're thinking about oil and water, why do they not mix? And there's a tendency to think of, the oil basically wanting to adhere to the other oil molecules. That's not really what's going on. What's really going on is that any water that's in the oil so much wants to be with the other water molecules that it separates from the oil. So the oil sort of ends up, oil molecules end up dancing with the other oil molecules because nobody else wants to dance with it, basically. The water molecules go off and dance with each other. So, all right. And I mentioned this in the notes. I think this picture is really an important one to keep in mind, that in these strongly polar systems, whether it's a fixed dipole that can then orient to give you a good attractive system, or it's just an induced dipole. So the way an induced dipole would work is you start with so you start with a system. These are both neutral with no permanent dipole. And actually these exert surprisingly an attractive force on each other due to what's called the van der Waals attraction. Basically, even though there's no net charge, if you take a momentary, there is motion of charge on the substrate, and there will be fluctuations in inhomogeneities. And so every so often, you'll end up with a slight preponderance of negative charge on one side of it and positive charge on the other side of it, just by chance. And at that moment, if you put an electric charge in space, there would be a force on that due to these two charges, and they wouldn't quite balance. And that non-balanced force actually can induce a dipole in a nearby object. So for instance, the positive charge here is going to tend to attract positive charges, is going to tend to attract negative charges. And the negative charge over here is going to tend to attract positive charges. But you can see now that these induced charges are perfectly oriented to give you maximal Coulombic attraction. And in fact, the effect runs away with itself because now this induced charge induces the right orientation here, right? So it acts back on itself, and then they start to approach each other, and as they approach each other, the fields get stronger, and so the polarity gets stronger, and you get a very strong, depending on the conductivity of the objects and their scale and so forth, it can go like r to the 6th, or I think r to the 4th, but you get this very strong attractive force between the two particles. So you don't need a permanent dipole to get a strong polar attraction. And even objects that are nominally non-polar, they'll still have some degree of van der Waals attraction between them. All right. And so actually the language I use here is wrong, right? I say in surfaces, polar liquids tend to repel nonpolar surfaces. But that's not really true. It's really that polar liquids tend to be attracted to themselves so strongly that they leave no room, so they effectively repel the nonpolar surface. All right. Any questions about that? All right. The other thing is if you're willing to sacrifice the wafer, like if you're just interested in if the process makes it clean or not, you can actually just breathe on the wafer and you can instantly see whether it's dirty or not. Just because your breath is warm and it condenses out on the wafer. But you know, it's going to put all sorts of horrible stuff on the wafers. Okay. One thing in terms of cleaning to try to remove particles, of course you can try to just blow dust particles off. But there are some contaminations, for instance, inorganic contaminations that are at the atomic scale. They're not going to just be blown off. Also, small particulates, due to these very, very strong forces, a small particulate has a very strong adhesive force on the surface and a very small surface area, so blowing it with air is not going to take it away. So the other thing is be really, really careful whenever you blow a wafer with air, because generally these nozzles that are in the labs have not been treated well. And often people will put them in resist bottles to blow a little nitrogen into the resist bottle, or they'll hold it too close to a wafer, and whatever was on the wafer comes out and redeposits on the wafer. So I remember, you know, in grad school we'd have these experiences with a clean wafer, and then you blow the dust off of it, and then if you do the breath test on it or the steam nucleation test, you see the lines of the nitrogen where it deposited junk on the wafer. So so blowing it with nitrogen is something you should do only in extreme circumstances. Also, the bottles that most bottled nitrogen comes in have a lot of oil in them. So if you are using nitrogen, you should of course use really clean nitrogen, like you would get in the clean rooms here. We use nitrogen that's boiled off from liquid nitrogen. It is very clean. But if you're doing it yourself, you should get a nitrogen dewar and then use the overpressure from the dewar to get your nitrogen rather than using a tank of nitrogen. Okay, so water is very often used to remove contaminations. There's a whole procedure I won't go into here for making deionized water. Basically, it's a process of killing the bacteria, removing minerals, and then physically filtering the sort of dead carcasses of the bacteria and whatever else out of it. And then you measure the resistivity, and if the resistivity is above 18 megaohms, then it's considered deionized, and then you can use it in your rinse tank to rinse your wafer. Be very, very careful when you do this, because deionized water, the reason it's useful as a cleaning contaminant is because it has a very strong energy of solvation for many, many materials. So if you have no ions in water, basically there's tremendous force pulling ions out into the water. And that will act on anything you put into it. So if you take say you're doing a liftoff in a hot liftoff solution, and then you go into this cold deionized water, that hot metal that you just deposited will be etched really strongly and corroded by the deionized water. So so there's a number of materials. This can happen to your substrate too. We just recently learned that magnesium oxide, which we've been working with for a long time, is etched by deionized water. And so luckily it hadn't been affecting the process, but we're considering adding a deionized cleaning step to the process, and it was recommended by the supplier of the material, and it seemed like a very innocuous thing to do. But before we did it, we first did a literature search and then checked ourselves and discovered indeed that magnesium oxide is etched by deionized water. Very low rate, but enough so in our case it would certainly have killed our devices had we undertaken that. So be careful when you're using deionized water. And the water that comes out of the taps in the clean rooms here at MIT is generally deionized water, labeled as such.
So is that also why people say it's bad you can drink deionized water?
I assume so. I would think that would be terrible, because it would, whatever in your mouth, I would think it would become ionized almost instantly as soon as it enters your mouth, but it would damage the cells in your mouth, I would think, because it would pull the ions out of them. But whether that's in fact true or not, it might be such a small amount of ions that it pulls out that it's just a little bit of the salt in your saliva takes care of it. I don't know. So there's a number of solutions recipes that have developed over the years for taking various organic and inorganic solvents out, contaminants out of wafers. So these SC1 and SC2 solutions that are used in clean rooms basically are a sequence of removing more soluble and then less soluble materials out of the wafers. The SC1 attacks the organics, and then the SC2 pulls these heavy metals out of the solution. Particulates are a big concern I mentioned before. So particulates are typically removed. Small particulates are very hard to remove, so typically they're removed by what's called megasonic agitation, which is megahertz scale agitation. It's very simple to do this. You can just take the wafer and put in a transducer in water that emits megasonic waves, and then shine it on the wafer, and it'll clean the wafer. The thing to be careful about, of course, is these are being removed because it's exerting tremendous forces on the nanoscale on the wafer, and so so you have to keep in mind that the wafers can be damaged and devices can be damaged by these processes. Another technique that is quite innocuous actually is a carbon dioxide jet. You just take expanding jet of carbon dioxide, it freezes as it expands, and it puts a fast stream of frozen dry ice basically on the wafer, and that is very reactive and removes, it is very effective at removing particles simply because these particulates have a substantial mass and collide with the surface. There may be a reactive component there too, I'm not sure. The one thing to be cautious about is storage in plastic. So all of these plastics have volatile elements to them, plasticizers and other elements that were used in their manufacture. And even the wafer carriers here all have organic contaminants that come off of them. So Professor Smith, who lectured a little while ago, did an experiment a few years back, and he basically showed that little stainless steel canisters are the best for storing wafers in. And I suspect that glass is pretty good too. The thing to keep in mind is once you've got a clean surface, it's actually not terribly easy to contaminate it. So if you have a clean surface and a volatile organic lands on that surface, because the volatile organic is not strongly attracted to the surface, it'll actually with high likelihood come back off. And what happens is eventually you get 3 or 4 such molecules that collide, and then they form a network that nucleates basically a contaminating sheet. And so you're safe for probably about 24 hours. If you've got a clean surface, it's going to stay clean for a certain period of time. Another method that we have available in our lab is the UV ozone cleaning. This is incredibly simple. It's basically just a UV lamp in a box. And when you turn it on, it creates ozone out of the air molecules, the oxygen out of molecules in the air, just because the line of the mercury lamp is resonant with one of the excitation lines of oxygen. And that results in the creation of these very reactive both ozone and atomic oxygen. And that atomic oxygen can then get into a carbon-containing organic and produce carbon dioxide, which is of course really volatile and off it comes. And so it can break down these organics quite effectively. So if you have a thin layer of contamination, it works well. What you do have to be careful is UV light is also effective at cross-linking organic contaminants. So if you took something like this and put a thick resist film under it, rather than removing the resist, it would just really, really toughen it by cross-linking all the carbon in there and creating something that was completely unremovable. So you should only use it with thin layers. All right. Before I get into the optics side of this, I'm going to actually switch to the next chapter and just go through this quickly as well. So, this is not the right version. Shoot. Okay, I finally found it. So, okay. So I already talked a lot about these forces. I'm not going to go through them again. But I do want to kind of go through this aside. And this is not in the version I handed out, but it is the version that's online, because I just wrote these notes. But the point here is that particulate contamination is really an overstated problem in most of the type of research that goes on at a university and the type of industrial work that's involved in prototyping and development.
Okay, so typically it becomes a problem in large-scale manufacturing, with a couple of key exceptions. So the one is if you're actually building a large-scale integrated system, meaning you have thousands of devices that cover large areas, where the active region of the device that's susceptible to contamination, is millimeters in squared. Okay, so you would not include here a single optical waveguide, say, that goes across a chip, okay? Because this is, if you look at the amount of area, this is actually a very small amount of the total device area. Right? But you would include a fully integrated nest with resonators and additional waveguides that comprise, if you looked at the area that might be destroyed by the presence of a wafer, that total integrated area might be more than a few millimeters squared. So if it's not more than a millimeter squared, it's typically not a problem. The other thing where it's typically not a problem is, where it could be a problem, excuse me, is when you take two surfaces and you try to put them into contact. So there's a lot of processes in lithography where you want to have a clean surface and another clean surface, and you want them to either bond, or you want to just have them in contact temporarily while you shine light through them, something like that, or to do nano imprint. So in these systems where you want them on top of each other, if there's a particulate, it will result in a buckling, a local buckling, and that, depending on how rigid the substrate is, that can cause a lot of problems. So let's suppose that we have these two substrates. If you have even like a 10 micron scale particulate in between them, it's going to cause a wedge if they're rigid. Okay? If they're not rigid, actually even this will not be a problem. You might get a local defect around it, but if they're compliant, they can actually still bond across them. So that's the other case where you really need like a class 10 clean room. I would rather in a lot, so there's course notes for next week. The spring break is next week, but there's course notes for the week after in the back, so please pick them up when you go out. I would personally rather have a well-trained technician or researcher than a clean room. If you imagine a clean room, you saw what happened when I shook my bag in front of there and you saw the dust coming up. Every researcher, everybody in the clean room is just exuding dust particles all the time. Even behind those clean room suits, they come out of the eye slits, they come out of the sleeves, they come out of the zippers, and I can promise you go into any class 10 clean room at any university in North America anyway, and everyone's walking around with their face masks only up to their mouth, not covering their nose, right? And so that nose is just, it's kind of disgusting, but it's just particulates coming out. So if you're standing up your wafer, all bunny suited up, your nose is just contaminating your wafer. You might as well just be out in space. Laminar flow helps you because laminar flow, there's this constant downward flow, and so whatever particulates do come out, I gotta stop doing that gesture. Whatever comes out, it ends up being carried down and not recirculating and having multiple chances to land. But also, even in a dirty environment, not every particulate that comes off is going to settle on your wafer, right? So I remember I visited the facility once that there was no clean room, just laminar flow hoods. They were making 1,000-element complex circuits with high yields at this place. And the technicians would all go out sort of once or twice an hour and have a cigarette break outside, so they were just, smoke was coming out of their cigarettes. It's terrible for your lungs and generate huge numbers of particulates.